Hello everyone. We will now start a session called Computational Modeling from Neuron to Cognition. So to start, I have the great pleasure to introduce Alexandre Gramfort. He's a research director at INRIA, a national research institute dedicated to science and numerical technologies. And he's also a co-director of the Center for Data Science in Paris. Alexandre did study mathematics, and then he did a PhD with Maureen Claire at INRIA to investigate signal processing of neuroimaging data. And Alex is specialized in machine learning and signal processing, and is one of the leading architects of the famous Python software MNE that you should all use if you want to analyze EEG or MEG data. Or maybe I should not say that, because I worked with Sylvain Baillet before. So Alex plays a fundamental role by allowing us to use methods that we don't understand. And today will tell us why deep learning should be used in cognitive and clinical studies employing EEG. And as an example of deep learning, you just heard a music that was created by a deep net. So please welcome Alex.
Thank you very much for having me, for inviting me, for organizing this awesome, friendly conference. Very happy to see a lot of friends that I haven't seen in real life for a while. So I had to find some catchy title to maybe attract people in this room. So that's maybe it's catchy, a bit provocative, and maybe make you skeptical. I'll try to convince you that yes, you can probably use somehow deep learning or statistical learning to make sense of EEG and learn something with it. So before I start, I'd like to maybe step back and tell you that at the end of the day, what you want to do with deep learning is to learn from data what people will call representations. And representations are pretty much everywhere when you analyze data, signals, or images. And what you see here is typically a spectrogram of speech. And basically this short time Fourier transform that you see is a way to represent the data in order to use it. We also have these types of wavelets on images, these types of maybe pictures you may have seen on the web. But also when you analyze diffusion MRI data, you work with this spherical harmonics that are also a way to represent the signal. And at the end of the day, once you have a good representation of the data, what it allows you to do is to look at the data in a meaningful way. It allows you to do denoising. It allows you to also have models that are good for prediction. Okay, so kind of the promise of deep learning is to find a way, and we'll see what are possible ways, of learning good representations from EEG or MEG data. So before I start, we wrote this review with a number of people a couple of years ago, where we tried to do a kind of exhaustive and exhausting evaluation of deep learning papers on EEG. And maybe one figure that you can find on this paper is this one that shows you that there's more and more papers that are using deep learning in some way on EEG for various types of applications. I would say very engineering stuff with BCI, but you see that, for example, sleep, we'll cover during this presentation, is also used. People have also started to use this for like predictions related to epilepsy data. So there's more and more activity at this. I'm not sure that everything is mature and ready to be used to answer real cognitive or clinical questions, but at least there's some activity there. All right, so 3 routes to deep learning. Right? So it's a friendly conference, so I try to put some jokes. So let's look at we'll see the first route, which is called the unsupervised way of learning from data. Then we'll look at the supervised way, and then we'll look finally at the self-supervised way. Okay, so we'll see what is behind these things. And now I'll basically develop in this talk 3 different way of learning representation with deep learning in these 3 settings. All right, so let me first start by what I call the unsupervised way, where we are going to try to learn motifs in signals completely without supervision, meaning that there's nobody that actually put labels on the data. We're trying to extract things using a statistical model that we'll try to develop. Maybe as a disclaimer, in this talk, there's a few equations. I could not resist. Hopefully, I will also come up with drawings to kind of make sense for this. But just a warning, just please don't leave the room if you see equations. So this work was mostly done by two former grad students that are, some of you know, so Mainak, who's now at MGH, and Tom, who's at UC Berkeley. So when we started to work on this problem, it was at the time where there was some interest in looking at waveform shapes. And just to illustrate the problem, what you see here is a mu wave, okay, that is well known to be found in the somatosensory cortex. And this mu wave that you see that shows this mu Greek letter, when you pass it through a linear filter that we use all the time when we do temporal filtering, you make this asymmetry disappear. And at the end of the day, the claim is that you make every signal like a sinusoid. Okay, so you have this picture that brain produces sinusoids. But one of basically the claim that you see here is that the way we filter data generates these types of a priori expectations. So the model that we've looked at is called convolutional sparse coding. And the idea is that you're going to take your signals that you see here. So of course, this is a simulated signal that is made by some motifs that looks like this weird shape, okay? And some activation that you see here in green that tells you when the shape appears, and the size of the bar tells you how much the shape has a strong amplitude, okay? So this model basically can be written mathematically as saying that your signal is a sum of different activations, okay? So the activations will tell you when the atom is appearing, and the D is the atom, okay? D stands for the atom of a dictionary, that's why it's called D. And basically this decomposition will decompose the data into when and what in the data. And so when you apply these things, for example, this is an LFP recording. If you apply these types of techniques on the data like this, the types of atoms that you see emerge is these three atoms where you see that you have a slow wave, where you have this high frequency wave that comes on top of the slow wave, and you see like one atom where you have the cross frequency effect, so the high frequency on the basically the edge or the top of the slow wave, or on the down phase. And basically these types of model allows you to extract these types of patterns and to give you a way to look at your data maybe in a slightly different way. So now this is only with one channel. We can extend these types of model to multivariate data like MEG or EEG, and this is what I will show next. And for this, I need to just do a quick detour by, I guess, what most people in this room understand, which is ICA, or at least you use it very well. Okay, so here ICA is basically saying that I'm going to take this data, that is real EEG data, and you're going to multiply this by a linear operator, a matrix, which would be called here the unmixing matrix, that will give you the unknown recovered independent sources. Okay, and this is produced by a software called Picard that maybe you should know. Okay, so at the end of the day, you have X, your data, and the sources that you want to recover. This is the idea of ICA. Sources should be independent. And at the end of the day, when you do ICA, what you're doing is that you're decomposing the data into A times S. A, in this case, would be the mixing matrix because it mixes the sources into the data, and the inverse of A would be the unmixing. But at the end of the day, when you do ICA, you're taking your data and you're saying that it can be extracted as a sum of a topography, okay, and a time course, okay? And then you look at the topography and say, okay, this is a blink, this is the time course of a blink. This looks more like a real dipolar source. This is probably brain. This is the corresponding time course. But at the end of the day, you decompose your data this way. When we do CSC, the idea is that we're going to change slightly the model of the time dimension by saying that every time dimension can be expressed as a prototypical motif, a temporal atom, and a vector of activations that tell you where in time, so when these motifs are appearing. So you're decomposing your data into topography that tells you maybe where in the brain, how it looks like in terms of waveform, and when it occurs. Okay, it's a different way of looking at the data. And now I'd like to show you some scary equations, just to give you an idea of what it means to solve this problem. The simple message is that you just minimize the cost function the best you can, okay? And this cost function will try to tell you that your data should be well expressed by this decomposition. So this quantity should be as small as possible. And then you have a regularization that tries to say that the activation should not appear all the time, they should be sparse. So only the atoms appear not all the time, like in a sparse or limited way. It's not really important how we do this. I'd like to illustrate what happens when you do these types of analysis. This is data following median nerve stimulation using MEG. And this is a typical atom that you can recover where you see these types of mu waves. And like to illustrate in this results is that if you look at the time frequency content of this atom, okay, the fact that you have a mu wave produces in the spectrum these two bumps, which are called just harmonics. Okay, so here this is a 10 hertz peak, but here it's really twice this 10 hertz, so it's actually probably closer to 9, so 9 it would be 18. And this is really the time frequency, so the power spectrum density of your atom that is not restricted to a certain frequency band. And here that would be the location, so just fitting a dipole to this topography, the same way you could do it with ICA, you can find where this atom is produced in the brain. Okay, so these types of tools, you can play with it, and there's a software that we call Alpha CSC. I don't know if it's because it's alpha stage, but it's still, I would say needs to mature, but you can try a number of things using already the software. Now I'll show you a few results. So if you go to this web page and you try to run this tool on here, this is the M&E sample dataset that contains audiovisual stimuli. Well, first you see that you can very nicely recover the ECG. So one motif that is extracted from the MEG is the heartbeats, and you see, so it's a very expensive way of getting an ECG. This would be the blinks, okay? And here now these are more evoked responses. So here this is auditory bilateral activations. This is more like lateralized and actually related to the visual stimulus. Here is also visual. And here you see some kind of way that looks more like a parietal source with also many harmonics that are emerging from the data. All right, so that was the unsupervised way because I did not provide any labels. I was just trying to decompose the data using, I would say, multivariate statistics and somehow similar to ICA, but with a slightly different expectation about the sources. They should be expressed by these motifs. So now I'm diving into what I call here the supervised way. And here, this is mostly the PhD work of Stanislas Chambon, where we looked at two tasks related to sleep research, to sleep EEG. And the first task that I will be covering is sleep staging. And I'll go back to this application now. Okay, so most of you, I guess some of you or a few of you in this room know what sleep medicine is. So EEG is used clinically for certain applications, and sleep is one of these clinically routinely used application. And the data that we'll play with are so-called polysomnography data. It has nothing to do with the football club in Paris. So we have this PSG data, and here we have multimodal data. We typically have the EEG, but we also have EMG, so chin electrodes, or EOG that are all recorded and available at the same time. And so there are two tasks actually on this data. The first one, you can see this as a classification task. People call it scoring or sleep staging or sleep scoring. And for me, it's going to be a multi-class problem where every windows of data needs to be assigned with a stage. But you also have another task that can be solved using machine learning, which is the detection of so-called sleep microstructure. So here, that would be here a spindle. Okay. And so here, this is classification, and this is joint detection and classification, and it is very close in terms of learning tasks to what people do to find objects in images. You want to know where it is, what's the size of the bounding box that contains the car or the bike, and the same types of technology that can be used to detect these micro events. So one way to formulate the problem is as is. So usually scoring is done by windows of 30 seconds. So the X, the data that is going to be the input of the deep learning system is a multivariate signal. So here, this is your observation that is called X. And what we're aiming to do using machine learning and, for example, deep learning is to learn a function. So it's learned, that's why you have this small hat, because it's estimated from a training data set. And it needs to be a function that will take this multivariate time series and that will output one of these 5 labels. So either you're awake, or you're in rapid eye movements, or in N1, N2, or N3. And typically, if you do these 5 stages, which are the most common, you have a 5-class classification problem. And so once you have framed the problem this way, it's actually very standard, I would say, machinery in terms of deep learning. I guess if you have the data and the labels, then people are like deep learning experts, they could probably already start to do useful stuff with it, except that they would probably, you need to explain to them what's the problem and how to clean the data and how to pre-process efficiently, that otherwise they would have no clue. So the idea of the contribution you've made here is to basically use some kind of a priori of expectation of what could be the content of value in order to do this staging, this deep scoring. So it's really signals, and in the end of the day, why people classify in certain stages is the frequency content, and this frequency content you can obtain them with temporal filters, but temporal filters are nothing more than temporal convolutions, okay? So what you could use here is a convolutional neural network where rather than using a Gabor atom or a Morley wavelet, you're going to learn a filter towards the learning task, the classification task. Then you could also say, I've got different different modalities. I've got the EOG, I've got the EMG, I've got the EEG. So why not processing these types of things differently? Because when you look at the data from a sleep expert, you read the EMG, you extract information about EMG, for example, the fact that you have facial movements that are specific to a certain stage. So we could basically implement this knowledge in the network. And also another thing that is very, I guess, natural when you understand these types of problems is that when you're in a certain stage at a given moment, it's very likely that you're also at the same stage just afterwards or before. So there's kind of a temporal structure. With all these intuitions of the data, you can come up with I would say, a deep net that you can therefore train, where it will do a convolution that depends on the different data modalities. Then it will do here a spatial filtering. Spatial filtering would be an ICA, a way to combine channels in order to maximize some kind of signal-to-noise ratio, but here driven by the learning task that you're trying to do. Okay. And this network basically will take your data X into a representation. So I talked about representation at the beginning. This representation, that is this vector Z, okay? And this vector Z potentially is everything that is needed to learn the label, here typically using a linear model. So here I've got a good representation. I could probably use a logistic regression with 5 outputs, and that should be enough if I have a well-trained representation. That's pretty much what we do. We try to learn end-to-end the representation Z, and we take also neighboring windows in order to learn a bit of temporal context in order to predict. Okay, so we've done some experiments. I usually work with public data, so hoping that people can replicate what I'm doing. So I use data from MAS, and it's collected in Montreal, and so it's 61 records. So it's not huge, but I guess enough to make our points. It's roughly 60,000 samples, so it means that you have 60,000 labels available. So 60,000 windows of 30 seconds annotated. So it's huge. Okay, so it's really orders of magnitude to standard labels that you have in other tasks. We pre-process in a certain way, and at the end of the day, the game is you learn on the training set, you find a way to set your hyperparameter using a validation set, and once you're done, then you look at the test set. Okay, this is really this train, valid, and test paradigm that you should be implementing. So we use 40 nights for training, 10 nights to stop the network training, hoping that we've stopped overfitting, we stop learning, and then we test on 10 left-out data. And we compare with, I would say, what people would do otherwise, handcrafted features, taking the mean, the variance, the Kolmogorov entropy of the signals, you feed this into another learning system, and you compare. Okay. Well, of course, if I show you this, it's because it works better than the others. Okay, this is result. There's many teams that are working on this problem. Okay, so there's many papers doing this. This is paper that is maybe 3 years old now. There's a lot more efforts trying to automate this. I give you the idea, but now and this is not really state of the art, but at least it gives you some flavor of what we did. And I think what is interesting is that probably the next slide, usually when I say a learning system is in practice, is very important. It's very interesting to understand when it fails. Okay, so the failure mode of your system is really part of the interesting part. Okay, the number at the end is yes, but can you tell me what is difficult? And you see, for example, that N1 is very often confused with REM. Okay, so these two stages are hard to discriminate, and this is really coming out of your experiments. And then we could do other fun things, which is that we're going to filter the data in certain frequency band and see how it affects the output. So you can see this as some form of ablation study. Okay, so you perturb the input signals and you see how the network reacts. And for example, you see that if you only keep, say, beta bands, so you only keep this frequency, then the system already predicts that you're awake. Versus alpha also has the same types of behavior. Now, if you keep other frequencies, okay, typically you only keep the delta part, then the network predicts that you're in N3. So it really learns kind of the scoring rules just from 60,000 labels on the data. Okay. All right. So the other thing I would like to briefly cover is this issue of joint detection, just to give you some intuition about how these things work. The idea is to basically predict the onsets, the offsets of each micro event. So the idea is that the system is going to try to start from a random window, make the window move to something where you think there is an event, and once he thinks there's an event, he will tell you what label this corresponds to, and that can be either, for example, a spindle or a K-complex. Okay. So we use this developed this technique called dozed, but it's very inspired by, I would say, really computer vision systems that are doing exactly the same types of images to detect shoes, bikes, or whatever stuff on images. We try to take the good things about this data. Maybe one specificity is that sleep data are really long signals, so it changes a bit what you can do compared to like a small image that you usually process. And the way you evaluate your models is to say how much what you predict overlaps with the truth, okay? Because the annotations from clinicians, they are not perfect. The onset is really sometimes approximate. So you need to find a metric that tells you, okay, this is probably not enough overlap. So this is going to be what you would consider a wrong prediction, and would be if you have enough overlap, that's a good prediction. And with this metric in mind, you can start to compare techniques, okay? And what you're hoping is that these six techniques have a really high precision and a high recall. So your recall is your ability to detect the micro events. Okay, it means that you don't miss a lot of micro events. And then the precision will tell you, among all the events that you detected, which are true good events. Okay, so if you have a good recall, then you find pretty much everything. And if you have a good precision, all the things that you found are properly labeled. Okay, and it's always a trade-off between recall and precision. Depending on your, I would say, application, sometimes you care about recall, sometimes you care about precision. And the F1 is just a geometric mean of the recall and the precision. So it's just one number to summarize these two. Okay. All right, so I cannot have a video, so I just took a screenshot of what could be the video. So here is an example of what the video could have been. So that would be an event that is missed. So this is the true label that it was missed, and this would be a good prediction. So you see that the system really outputs the onset and offset of the micro events. All right, an interesting result that you see here is that these systems are not limited at all to one class. So you have the same system that can do also either K-complex and spindles at the same time, so can do multi-output classification. All right, so if you want to play, there's this software that is, so this work was done in collaboration with the DREAM company. So the Stan Chambon was a PhD that was supervised by me and the research team at DREAM. And so this is why this is in the DREAM organization. And this code that probably still works, hopefully. Okay, so now I switch to the last part, almost the last part I would like to cover, which is called self-supervision. One of the issues with ICA, one of the issues of unsupervised learning is that it's really tough to set hyperparameters. It's really hard to know what are the number of components, so it's like clustering, okay? You get clusters, you get numbers. At the end of the day, you have no single figure of merit that tells you if you did a good job. Okay, so unsupervised learning problems are interesting, but they are a major pain to disseminate and deploy because you have no easy way of kind of maybe automating certain settings of the parameter because of this no supervision, absence of supervision. And so there's something that for me is like extremely smart. It's called self-supervised learning, and it's a way to turn unsupervised problems like labels, data with no labels, into something that has supervision. So this is the work of Hubert Banville, who was supervised by me and working also part-time at Interaction in Canada. So the idea of supervision is the following. Here, imagine that I give you an image. Okay, this is a tiger. You take the image, you take some pieces of the tiger, you shuffle the pieces, and you ask a deep net to undo this random transformation. Okay, so you take structured data, you mess around with the data, and you tell a deep net to output this. And so if the deep net understood that the head of the tiger should be at the top, that the leg should be at the bottom, then it can do the task. And so the idea is that this task is a way to learn fairly abstract representation of the data without actually supervision. You just took the image, applied some random transformation, and you let the system do this. So the question we had with Hubert is, can we come up with similar tasks on EEG? And so one of the tasks that what we propose is what we call relative positioning. And in the context of sleep, you can easily understand what it does. I'm going to give you 2 windows of 30 seconds. And since windows that are close in time are very likely to come from the same sleep stage, then I'm going to say that 2 windows that are sampled close in time are going to be positive pairs. And now if I take 2 windows of 30 seconds that are, let's say, more than 4 minutes or more than 10 minutes away, they're going to be negative pairs. And so I'm going to train a deep learning system that will take as input 2 windows, 2 images, and it will output, are these 2 windows close in time or they are far in time? Okay. And by doing this, you end up with a classification problem for which you can do cross-validation, you can set the hyperparameters, whatever system that allows you to predict well on new pairs of windows if the windows were close or they are far in time. Okay. So we did this on 2 problems, on sleep staging and also the TOH dataset, which is a huge EEG dataset that is here labeled as normal or abnormal. So this, at the end of the day, if we learn a good representation using what is called this pretext task, okay, this relative position is called the pretext task. If we learn a good representation, we should be able to do this classification problem here at 5 classes or here 2 classes. Okay. So just to give you an idea, just the PC18 dataset that we use is almost 1,000 nights. Okay. And here TOH is really clinical EEG, like a huge public data set that almost has 3,000 clinical recordings that are publicly available. And so once we do this, if I just look at the Z vector that I showed you before, so this representation that is learned by the deep net, and I feed this into a logistic regression that classifies among the 5 stages, what you see is that if I have very few data points, if I only have, let's say, 10 windows of 13 seconds of data, I can already predict reasonably well, okay? Whereas if I were to take a system that was trained completely with in a supervised way, using the labels of all the data points, here I only have access to 10 labels per images, so it's not very time consuming, versus the opposite. Then if I have very little data sets that you maybe find in medicine or clinical context, then you can already learn reasonably well, okay? Of course, when you have a lot of data, then suddenly the supervised problem becomes more relevant. Okay, but you need to be in a setup where you have enough labels. And we can do the same thing with TOH, where here we predict normal or abnormal. Now, for me, what was really fascinating in this work is to say, let's look at this embedding. Let's look at the representation to see what it contains. And so what we did is take all these windows of 13 seconds, we pass them through the network, and at the end we get this vector Z, okay, maybe a dimension 100. So every window is a vector of dimension 100. And from this, we can do some kind of nonlinear PCA. Okay, I don't go into the detail, but we project this data set in dimension 2, and we look at what it contains. So every dot that you see here corresponds to 1 window in the data set. And the color here, or what you see here, is colored by the stage, the sleep stage. So what you see is that all the dots that appear in the embedding, so in this Z representation, all these blue dots, they are corresponding to awake window. So you are more in this position of the embedding. Then when you start sleeping, you go along the embedding until you're in deep sleep. And then here you have REM, which is here in between. So really using absolutely no supervision, just this trick of pretext task, am I close or far, you can learn a representation that recovers the natural structure of what we know about sleep stages. And we could do this also using age, okay? So if you color the data now by the age of the subjects, okay, you see that in the embedding, okay, you have rather the young subjects which are in this part of the embedding, and then the old subjects which are more in the inside part. Okay, so again, without supervision, you can recover some kind of hidden latent structure in the data. All right, we can do this with TOH. So here, TOH, we color by the labels, pathological. We can also color by the gender, okay? And you might wonder, why do I have these blobs here? And it turns out that TOH, to have 3,000 clinical data set that was recorded over years of acquisition, and these, I would say, islands of data points are coming from different acquisition systems. Over time, the acquisition changed, and that creates some bias, that creates some like differences in the acquisition that you see revealed by the system here. You know, so these are basically, if you were to color the data by the time it was acquired, you would see the latent structure. Okay. So now I'm done with my 3 things, and since I have plenty of time, I'll spend a few more minutes to talk about this force route. Here's something that has been very recent, so this is kind of ongoing work. Where we use deep learning to solve Bayesian inference. So this is the work of a postdoc in the team who just got a position at INRIA, so Pedro Rodriguez. And the idea was to look at what people call simulation-based inference. Has been used in many applied science, like in physics a lot. And the idea is to kind of solve this, I would say, Bayesian inversion task, where you try to find the so-called posterior. You try to find the parameters of your model. What you have is the data, okay? So you have here a term that people call the likelihood, okay? This is how likely is the data given the parameters theta. This would be your prior, and this would be the evidence, okay? And when you look in biophysical model, okay, you can find some approximation that allow you somehow to have sometimes a tractable likelihood, but very often you don't. But what you can find, and you can find more and more these days, and I think Stephanie Jones will talk about this afterwards about HNN, you have a lot more these simulators. So what you don't know how to invert the system, but you know how to simulate it. There's been a really important effort over the last 2 or 3 years, because there was like a nice discovery in deep learning called normalizing flows. And this allowed people to solve this problem using a deep learning, where the only thing that you know is how to simulate data. Didn't put the ref, but it's really something that's been pushed by the group of Jakob Macker in Tübingen, and he's been using this for other types of neuroscience, and we've explored these ideas using EEG. And so, real quick, this is more not aiming to show you how it works, but just to give you a flavor of what we can do. So this is EEG data, okay? So either using eyes closed or here eyes open, okay? It's coming from a public data set that you can find on Zenodo. And here, if you just look at the power spectrum density of either the observations of type eyes closed or eyes open, you have these power spectrum densities where you see that the alpha appears when you close your eyes and is absent when you start to open them, which is kind of, I guess, very expected. And so what we wanted to know is how much we can use these types of non-invasive data to go to physics and the biophysical parameters of a well-known model. So for this, we took the Jansen-Ritt model. So I know that people in this room have worked on this. I guess I should talk to you. But so we take this stochastic Jansen-Ritt model. So we have a simulator, okay, that is basically implemented from this paper, taking the model, the stochastic model from here. At the end, we have 4 parameters. I will show you why we have 4. The first is the connectivity between the excitatory or the inhibitory neurons, okay? Here, there's the statistics of the incoming oscillations from the neighboring cortical columns. And G is the gain factor, because you don't know how far you are, you don't know how far the cortical column is from the EEG. So here you can see this as a confounding factor that tells you how much the signal is attenuated between the cortical column and EEG. And for us, it's a big problem, because either you say, I solve the inverse problem and then I fix this, but finding amplitudes using inverse problem is not really so easy. Or we treat this gain factor as a confounding factor that we'll try to marginalize or remove. And so this is a type of result that we obtain. So you see posterior distribution, which are fairly complex, and this is allowed by the generic nature of a deep density estimator that allow you to get a posterior on your different parameters using only one windows of data. But you can, with the kind of our contribution is to explain how to leverage multiple observations from the same model, assuming that the gain is a shared parameter. And what you see is that you get much sharper posteriors from this data. And for example, you can see that the C parameter, which is known to control very much the presence of alpha and the presence of like clear oscillations, is revealed by the system. You see that the C parameter, the posterior is very concentrated. And what this tells me is that, well, we can really use the C parameter. We can really interpret the C parameter as something that can be inferred from the data. Whereas if I would give you a posterior like this, there's a lot of overlap, and it's probably unclear that the posterior estimate can be of any belief. All right, I'll conclude by stepping back. It should have been a video, so I apologize. And I will not do it myself. So John told you all models are wrong, but some are useful. I will tell you something a bit different. I will tell you that all models are wrong, but some are coming with software that you can actually use. So there's been a lot of work over the last 10 years, 11 years, working on the MNE Python software that you can see here. This is the commercial part of the talk. Okay. Just to give you an idea of working with sleep data now these days with MNE is fairly simple. This is the PhysioNet's sleep data set. You read the polysomnography, you read the hypnogram, which is an EDF annotations. You set the annotations, you get events, you get your epochs, and this is just extracting epochs of wake stage and plotting the PSD. Okay, so hopefully they should make processing this data much easier than it was before, at least in Python. Over the last 2 or 3 years, we have a joint funding with the group of Tonio Bol in Freiburg to try to bring deep learning to real people. This is this effort with this software called Brain Decode, which is a glue between MNE to get access to EEG data, scikit-learn for the API, and PyTorch for all the deep learning machinery. In this software, you can find a number of examples that hopefully should run on your machine. You have the tutorial that explains to you how to use the sleep staging system that I showed you before, the work of Stanislas Chambon. You have another example that tells you how to use this self-supervision, so this relative positioning task. And this is an example that, of course, is only on a subset of the data because this is produced automatically on GitHub. This is really updated dynamically by machines in the cloud. And I think that's it. So thank you very much for your attention. And if you have a few questions, do not hesitate. Thank you very much. Yes. I will repeat the question, I think. So the question is, what do you feed into these deep nets? Do you feed the raw time courses, or you feed, for example, the time frequency representations? All these works use the time series, but there's especially state-of-the-art networks on sleep are using typically both. They feed the time courses. Mostly the group of Martin De Vos is heavily pushing these types of ideas. Where you combine the kind of more global aspect of the time frequency and also the raw time courses, and you can basically train a deep net that in parallel will process either the time frequency and the raw time courses, and at the end combine the decision to make maybe a more informed decision. Yes. So the question is, how do you choose the architecture? I try to kind of motivate why we choose these types of convolutional neural networks. For example, on sleep, people are using also these recurrent modules because you have some neighboring structures, so it's more like a sequence prediction. So for these, people use recurrent net. I think it's really a lot of trial and error. What brain decode, in brain decode, you have a model submodule that contains predefined architecture that have been tested and published. For example, you have EEG-net, EEG-net v4, you have the so there's a number of architecture that have been published for different problems, and we try to provide this architecture. They're not pre-trained, but at least you can retrain these models. And one of the idea of brain decode is also to use these models as a model zoo, where you could put this architecture and people can actually test. Because re-implementing all the time the work of others is time consuming. So if we agree of where to put all these networks, then we can probably start to compare and maybe agree about how to share pre-trained models, which I don't think we're there yet. So M&E, I would say, is fairly a mature software. Brain decode is still a young and learning from, I would say, along the way. But yeah, if you want to have a look and complain because it doesn't work, I'm pretty sure that some grad students will be happy to help. Yes?
I have a question on the amount of data that you need for this supervised method. So it's not very large data set.
Yes.
If I have an experiment with, let's say, 20 participants, 2 classes, half an hour of data per class, can I still use supervised method?
To be honest, I haven't seen a lot of very convincing use of deep learning for these types of cognitive paradigms. So I would say maybe when we start to have pre-trained models, it starts to make sense. But to be honest, for this scale of data, and there are simpler stuff to do with M&E. I guess the idea is that you try and you compare with something that first you do the matrix linear algebra and you diagonalize matrices and you see how it works, how good you are with spatial filters using whatever CSP or XDAWN or these types of fancy but still very approachable and very fast to compute techniques that have been developed for BCI or say BCI is from one message I tend to repeat is like if you want to really do multivariate analysis of your data, look at what people have done in BCI for the last 20 years, and you realize that there's not much left to invent. This is it. Thank you very much.